Right. Like I said last time, we are going to be learning how to use properties of logarithms to differentiate some really complicated looking function. Now, here's the idea. Remember that log of products become the sum of the logs, and log of division becomes the difference of the logs. So, log of f of x times gx over hx can be rewritten as log of fx plus log of gx minus log of hx. And the nice thing about that is if I take the derivative of log of fx, then it's just f prime x divided by f of x. So it comes in handy as a tool for finding certain derivatives. For example, if I have to differentiate this complicated looking function here, y is equals x to the 3/4 square root of x squared plus 1 whole divided by 3x plus 2 raised to power 5. You could use product rule, quotient rule, but it would really be super tedious to do this. An easier way to approach this would be to take logarithms on both sides so that ln y becomes ln of this entire mess, which then can be rewritten as log of x to the 3/4 plus log of x squared plus 1 to the 1/2, because square root means a power of 1/2, minus log of 3x plus 2 all raised to power 5. Now we can use a property of logarithm which we saw before in the previous video, where the exponent can be converted into a multiplication. We get log of y is 3/4 log of x plus half log of x squared plus 1 minus 5 log of 3x plus 2. We take derivatives on both sides. We get 1 over y times dy over dx becomes 3 over 4 times 1 over x plus 1/2 times 1 over x squared plus 1 times 2x by using the chain rule, minus 5 over 3x plus 2 times 3. Multiplying both sides by y, because we are trying to isolate dy over dx, we get dy over dx equals y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. So as you can see, a pretty complicated derivative, a derivative where you have to multiply it by y, which is itself this complicated starting point for the problem, right? So taking logarithm really helps finding derivatives of functions like these. Now you may consider this to be a really, it's a very unnatural looking function that has been made for this purpose. But there are certain functions like the one that we're going to look at next, which are not that unnatural. And this is the only way in which we can find the derivative of these functions. For example, consider y equals x to the power x. Now the base is changing and the exponent is changing. So you cannot use product rule, you cannot use the exponent rule, or any of the other rules of derivative finding for this particular function. The only thing that we can do is take log on both sides, end up with log y is x log x, take derivatives on both sides. Y prime over y is ln x plus x times 1 over x by product rule. So y prime is 1 plus log x times y, or y prime becomes x to the x 1 plus log of x. Now recall in the previous week videos, I said that one of the definitions of E that I really like is that it is the limit as x goes to 0 of 1 plus x whole raised to 1 over x. Now, with the knowledge that we have gained so far, we are able to prove this. Here's how the proof goes. Let the function y be ln x, f of x be log of x. Taking the derivative gives me f prime x is 1 over x, or specifically f prime 1 is 1. But I can also write f prime of 1 using the definition of derivatives as this limit h goes to 0, f of 1 plus h minus f of 1 all divided by h. Now h is just a variable. I can replace that by x and rewrite it in terms of x. F of 1 is 1, and f of 1 plus x is log of 1 plus x. Log of 1 is 0, So this is actually just log of 1 plus x divided by x, which by the log property becomes log of 1 plus x all raised to 1 over x. But I know this derivative is 1, which means that the limit x going to 0, log of 1 plus x to the 1 over x is 1. Or the limit of 1 plus x to the 1 over x is e. Because to get rid of this log, I just have to raise both sides to the power of e. Right, so it's a neat little way of showing that this limit equals e. Okay, that's going to be the end of this video. Next video, we're going to look at examples of exponential growth and exponential decay.